Good morning everyone, Dr. Nat here. So we are still continuing with module number 5. This is the last part of module number 5, which is on random variables and probability distribution. So let's head over to our last part. Okay, so I want you guys to imagine a scenario. Imagine choosing a student at random from a list of all students registered at UPM and measuring the student's height and weight. Meaning to say our population is now the students registered at UPM, and from this population the outcome will be the height and also the weight, pairs, right? And this pair is our x and y, or our random variable. So each individual in the population corresponds to two random variables, which is the height and also the weight. Now our outcome is not limited to one or two outcomes. Sorry, it's not limited to one or two random variables. It can be more than two random variables. It can be 3, it can be 4, it can be 5. But for the sake of the syllabus and to make our life easy, we're just going to talk about two random variables. Okay, so in principle, any number of random variables may be associated with each item or each outcome in a population. So when two or more random variables are associated with each of this outcome, we call this as jointly distributed. Okay, so if all the random variables that we select or we want to know is discrete, then we would call it jointly discrete, and vice versa. If it is a continuous random variable, then we would call it jointly continuous. Okay, so let's go over an example. The values p, x, y give the probability that outcomes x and y occur at the same time. So this is part of the definition. You have your joint distribution, p, x and y, they occur at the same time. So it means that the probability of random variable x equals to some value and random variable y equals to some value. They occur at the same time. So if a student registered in UPM is chosen at random, the x represents the height rounded to the nearest centimeter, and the y represents the weight rounded to the nearest kg. Now, the keyword here is rounded. So remember, if we are talking about discrete, we would have gaps, right, in between our outcomes. And if we are talking about continuous, then we wouldn't have that gap. We would have intervals, because all the values within that interval is fair game, or it can be an outcome. So if we are rounding up the values up to the nearest centimeter or up to the nearest kilogram, we would call this jointly discrete. Okay, so ignore this. So here we are finding out what is the probability that 170 occurs at the same time with 60. In this case, our 170 is our x, which is the height, and our 60 is the random variable y, which is the weight, right? So here I want to know what is the probability that the student that I chose is 170 in height, centimeter, and also 60 kilograms. Okay, so if we are talking about a discrete random variable, then we would call the probability as joint probability mass function. Joint probability mass function. Previously I told you it could be jointly discrete or it could be jointly continuous. That was referring to the x and y when we're talking about this guy. So if x and y are both discrete, then they are jointly discrete. If x and y are both continuous random variables, then you would call it jointly continuous. When we're talking about discrete functions, we would call this joint probability mass function. Okay, so let x denote the measured length and y measured width of a plastic tray. Okay, so we have a tray. It looks like this. It looks like a paper, but it's actually a tray. So this is our width, and this is our length. Our width is our y random variable, and our length is our x random variable, because our length is more lengthy. Therefore, this is our x. Okay. So the possible values of x are given as 129, 130, and 131. And the possible values for y is 15 and 16. So if I were to write down the outcomes for my sample space, I would have pairs, right? and the pair would be 1 to 9, 15, 1 to 9, 16, 130 or 130, 15, 130, 16, 131, 15, 131, and 16. So this is the outcomes in my sample space for this particular experiment. Okay, so let's just call this sample space. Okay, so here I'm listing it out in a table. So I have 1 to 9, 50, 1 to 9, blah blah blah, the outcomes that we already listed earlier, and they've given us the probability that x, random variable x, is equal to some value and random variable y is equal to some value. There is a word n over here, which means that it occurs at the same time. You cannot have it separately. Okay, so 1 to 9, when the tray is 1 to 9 and 15, it has a probability of 0.12. When the tray is 1 to 9 and 16 in width, it has a probability of 0.08, and so on and so forth. So the joint probability mass function is the function of probability xy. So for example, we have probability 1 to 9, 15 is equal to 0.12, and the probability of the tray being 130 and 16 is 0.28. So this is our joint probability mass function. Okay, so exercise. Find the probability that a CD cover has a length of 100. Sorry, I said earlier it was a tray. Forgot. Find the probability that the tray has a length of 129 millimeters. So we know that this corresponds to our x random variable. We want to find out what is the probability when x is equal to 1 to 9. So here we have our P of x equal to 1 to 9 millimeter, which means that I have to add up all the probabilities when x equals to 129 happens. Okay, so we would have this guy and this guy. So it would become P, the probability when x is equal to, it would be like this. P 1 to 9, 15 plus with P of 1 to 9, 16. So whatever the probability that is, you add them, put it inside this equation, plus with 0.08. So the probability that your x random variable is equal to 129 is equal to 0.20 or 0.2. Okay, so find the probability that a CD cover has a width of 16 millimeters. So now we are talking about the y. The y random variable is equal to 16. So the same case over here, let's do it again. So probability where random variable y is equal to 16 would be whenever the random variable happens. Okay, so this would be P of 1 to 9 when 16 happens, plus with probability of 130 when 16 happens, plus the probability of 131 when 16 happens. Okay, so this would be, what is the value here? 0.08 plus with 0.28 plus with 0.04. Going to try to do my math here. 0.28 plus what? Please, with 0.08 is equal to 0.36 plus 0.4. You would get 0.4. Okay, so this is your probability, 0.40. Sorry, I'm stuttering. 0.40. Okay. So what does that mean? It means that the probability when your random variable x is equal to 1 to 9 is 0.20. You don't have it in the table because it is a summation of a few rows, right? And for the probability where y is equal to 16, you have to add up whenever y is equal to 16. Fairly easy, straightforward. Okay, so remember that we summed up when P is equal to x equal to 1 to 9, and also the probability when y was equal to 16, right? And we found out this one as 0.2 and this one was 0.4. So you have it over here. Probability of x, function of x, is 0.20, which corresponds to, over here, it's adding up all the probability when 1 to 9 happens. Doesn't matter what y is, it's adding it up all together. And let's see if it matches this one. What is the probability when y is equal to 16, which means that we add up all the probabilities when y happens is equal to 16. So when y happens is equal to 16, we add up for all the values of x's, it is equal to 0.4. So it is the same as what we calculated before. And what do we call this thing? This thing is known as the marginal probability mass function. Marginal. Why is it called marginal? Because you have it at the end of your table. At the end of your table, and it corresponds to your either your x random variable, or it corresponds to either your y random variable. Okay, so the probability mass function of y appears at the bottom row and is obtained by summing down the columns. Note that the probability mass function of x and y appear at the margins of the table, therefore the name. To summarize, if x and y are jointly discrete random variables, we're talking about discrete here, the joint probability mass function x and y is the function of probability x and y given probability random variable x is equal to some value and random variable y is also equal to some value. They happen at the same time. And when we're talking about marginal probability mass function of x and y, it means that we care about only one random variable. Even though we have a joint probability mass function, we only care about one. So what do? If I care about x, let's say I want to find out the marginal probability mass function x, I write it down like this. I only care about x. What happens? I have to sum up for all the values of y. So sum up for all the values of y given that x is some value. If I care about the marginal probability mass function of y, which means that I care only about y, I have to sum up for all the values of x that we did before, right? So I care about y, I sum up for all the values, for all the probabilities of x's at a given y value. Okay, so the joint probability mass function has a property that the sum of the x's and the sum of the y's is going to give you 1. So if we were to add up the values for this table, we would find out that it is equal to 1. So let's see. So I'm summing up for marginal probability mass function x, it would be equal to 1. 0.2 plus 0.1 plus 0.7, 1. If I'm finding out the marginal probability mass function for y, I would also get 1. 0.6 plus 0.4. That is equal to 1. Okay, since we have already learned about joint probability mass function and also marginal probability mass function, it's just fair game to learn about continuous version of it, right? So the continuous version of joint probability is joint probability density function and also marginal probability density function. So the difference in the name is this part over here. One is mass, the other is density. Okay, so if x and y are jointly continuous random variables, now we're talking about continuous random variables here, with joint probability density function f. Just now it was pxy. This was for discrete. Let me just put it over here so we can just compare. And a is less than b, meaning to say b is a number greater than a, and c is a number less than d. Therefore, if we are going to find out what is the probability of random variable x between a and b, and the random variable y between c and d, therefore we have to integrate two boundaries, right? So one boundary is from a to b, the other boundary is from c to d, and this is our function. Our function is a function of two variables, which is x and y. So here, look at it carefully. Your y is actually for this boundary, your x is actually for this boundary. So you put your dx outside, your dy is inside, even though you put your boundary for x as your first one. Okay, so let's assume there is a bracket here, even though there's no bracket. So this is how you can remember it. Remember, there is a bracket. Okay, so remember our discrete, when we're talking about discrete, we have something at a given value, because discrete always talk about when the value is equal to some value or not. But when we're talking about continuous, we talk about intervals. So this is why we have intervals and also boundary for our integration. And remember, the sum of all our discrete, let's say we were talking about the marginal probability mass function of x. For x, it would be, the sum of this would be equal to 1. And for py, it would be equal to 1 as well, right? Because it will always be equal to 1. The same case over here, if you are integrating this function from minus infinity up to infinity, which means that you're taking into account the entire curve or the entire function, the area under that curve or that function is always going to be equal to 1. This is how you validate if it is legit or not. Okay, so to summarize, if x and y are jointly continuous with joint probability density function fxy, then the marginal probability density function of x and y are given respectively by, same case over here, if we are talking about marginal probability density function for x, we don't care about y, therefore we are going to sum up for all the values of y. If we are talking about marginal probability density function for y, we care about y, we don't care about x, therefore we are summing all the area, so summing for all the values of x. Same case, we were summing with respect to y. In this case, we were summing with respect to x, because we only care about y. Same case over here. Okay, so if you are talking about dy, let's say your y boundary goes from c to d, therefore you would replace this boundary with c and d, even though you want to find out what is the marginal probability density function for x. And if you are integrating with respect to x, use the interval for x, which is a to b, even though you want to find out for y. Okay, so example. Okay, so assume that for a certain type of washer, both the thickness and hole diameter vary from item to item. So we have two random variables here. One is thickness and the other as the hole diameter. Let x denote the thickness in millimeters and let y denote the hole diameter in millimeters for a randomly chosen washer. I think washer is a type of part, not really the washer like a washing machine. Okay, assume that the joint probability density function of x and y is given as, this is our probability density function, if x is greater than 1 or less than 2, and y is greater than 4 and less than 5. This is the function. If otherwise, it is 0. Okay, so find the probability that a randomly chosen washer has a thickness between 1 to 1.5. So our thickness is x, 1 to 1.5, so this is x, and a hole diameter between 4.5 to 5, so this is our y. So is x between the interval where our function exists? Yes, good. And a hole that is 4.5 to 5, so it exists within the function that we have over here. So write down probability of x greater than 1 or less than 1.5 and the probability of y less than 5 or greater than 4.5. So your boundary, let's see. So you have your function over here. I'm going to start with boundary x. So 1.5 to 1 to 1.5, and I put in my function and I'm integrating it with respect to x. And then for my y, it is from 4.5 to 5. I am integrating the same function but with respect to y. So I'm putting that little bracket over there for your reference. So Same case over here. Let's do the integration slowly since I have time. If you need some recap on integration. Okay, so I've written down the function and the boundaries. This is the boundary for y, this is the boundary for x. I put out the 1/6 outside the boundary because it's just a constant and you can just multiply it later on. Okay, so I'm going to integrate this with respect to y first. I start with something inside first because it's in the bracket. So assume we are integrating with respect to y, right? So you need to assume that your x is a constant. So how do you treat a constant in integration? Let's say this is x is number 2. What happens when you integrate 2? It becomes 2y, right? But in this case it's x, so it becomes xy. Okay, so xy. So xy plus y squared over 2. And you put in the values from 4.5 to 5. Okay, so substituting 5 for y, I would get 5x plus 25 over 2 minus with 4.5x plus with 4.5 squared over 2. So I'm gonna cheat a little bit and use my calculator. Actually, it's not cheating. We engineers use calculators anyway. Okay, so 5 minus 4.5 is a no-brainer, so that's a 0.1 over 2x, right? Because it's 0.5. And then 25 over 2 minus with 4.5 squared over 2. Minus 4.5 squared divided by 2. Can I get that in a fraction form? So it's going to be weird. So using my trusty calculator, I got 19. 2 times 8 is 16. 16 plus 3 is 19. 19 over 8. So 19 over 8. Okay, so we're not done yet. We still have this constant. We can multiply it now or we can multiply it later. I'm going to do it later. Let's see what happens. Okay, so 1 over 2x plus 19 over 8. Now we have to integrate it with respect to x, right? I'm going to do this in the next page. Okay, so my job is not done. Let's do this. So we need to integrate with respect to x now. So this is what we have. 1 to 1.5, sorry, a little bit messy, dx, and we still have the 1/6 outside. So we need to multiply it at the end of the day if we want to make this correct. Okay, so 1/2x, integrating it with respect to x, I would get x squared over 2. So 2 times 2 is 4. And 19 over 8 with respect to x is just a constant. So I would get 19x over 8. Right? And I have to multiply this with 1/6. I can do that now or I can do that later. And I have to find out between 1 to 1.5. Okay. So if my x is 1, I need to start with 1.5 first. So 1.5 squared over 4 plus with 19 times 1.5 over 8. Okay, bear with me. And then you have your 1/4 plus with 19 over 8. Then you have to multiply all of this with 1/6. Let me use my calculator and get back to you guys. So using my calculator, I got 0.25, which is also 1/4. Let's see if it's the same answer. Ta-da! It's the same answer. So, great. So we can move on from this example. Hopefully everyone understands how to do integration when you have two boundaries. One for x and one for y. And you have a constant. You can multiply it inside the bracket, or you can wait until the end. You're done with all the integration and you multiply it at the end. That also works as well, which is what I demonstrated just now. Okay, so don't get confused. Recap on your integration if you forgot already. Let's continue with the next example. Now, we already know what is our... What were we finding just now? We were finding if the probability, if our random variable x is between 4.5 is between 1 to 1.5, and if our random variable y is between 4.5 to 5. Now it's asking us, find the marginal probability density function for x. So if we're trying to find for x, what do? We sum up for all the y's. This is for discrete. For continuous, we have to find out with respect to y, right? So whatever function that we have, we need to find it out with respect to y. So y that goes from minus infinity up to infinity. In this case, our boundary for y is from 4 to 5. So you put in 4 and 5 over here. Okay, so we are integrating our function with respect to y from the boundary of y, which is 4 to 5. So this is easy, it's just one boundary here. Okay, so here they put in the function. So xy, we are integrating with respect to y, right? So it becomes xy plus y squared over 2. Y squared over 2. And then you multiply, or you just put it outside this thing, and you find out what is the value between 4 to 5. Let's do it. So xy plus y squared over 2. I'm trying to find out between 4 to 5. This is integration with respect to y. And this is my 1 over 6. So 5 of x plus 25 over 2 minus with 4x plus 16 over 2. So 5x minus 4x is just x. 25 over 2 minus with 16 over 2, I would get 4 plus 5 is 9. So it would become 9 over 2. I still did not multiply with my 1 over 6 yet. So this is my final answer. And I put it here. 4x is between 1 to 2. Because why? We're talking about the probability density function, the marginal probability density function for x. When we're talking about the marginal probability density function for y, then we would talk about for y when y is 4 to 5. But we would be integrating the function with respect to the boundary of x. So x goes from 1 to 2, if I'm not mistaken. So our lower boundary, x goes from 1 to 2, correct. So going back to that function, so our minus infinity to infinity just covers 1 to 2. So you put in the function 1 over 6 x plus y, and you integrate from 1 to 2 with respect to dx. Okay, so let's do the integration together. So we are integrating the same function but now with respect to x. So x squared over 2, I'm putting the 1 over 6 over here, x squared over 2 plus xy or yx, and it goes from 1 to 2. So if I put in the values here, 4 over 2 plus, this would be 2y minus with 1 over 2 plus 1 y. So it's just y. So over here, I don't have enough space. Okay, 1 over 2 plus y. So this one, 1 over 6. So 4 over 2 minus 1 over 2 is 3 over 2. 2y minus y is just y. So you get 1 over 6, 3 over 2 plus y. And this is the function, the marginal probability function for y for when y is between 4 to 5. We're talking about y here, so we talk about the interval of y as well. Okay, so I hope that is clear for everyone. So that is the end of module number 5. So your test will cover up until this content. Please do exercises at your own pace, at your own time. Try your best to understand the content clearly. It doesn't matter which textbook you use as long as you do the exercises related to the syllabus. And I will see you on the test day itself. Okay, so I'll see you guys. Bye-bye. Take care, everyone, and study well. You have around 4 days, 5 days to study. Bye-bye.